very nice. So now we have Ileyk.
Can you see my screen?
Yes, perfect. Okay, Ileyk El Mellah will talk about morpho-kinematics around cool evolved stars.
Thank you, Katarina, and thanks to the organizers for this occasion to share recent work concerning the morphology, indeed, of like the circumbinary envelope around cool stars. So for the last couple of days, we have heard like amazing results concerning the early stages of stellar evolution. So for instance, on protoplanetary disk. Now let me take you to the end of the story when a star leaves the main sequence to become an asymptotic giant branch star, or further a red giant or red supergiant, depending on its mass. So in the last years, thanks to the VLTI, several teams managed to resolve stars other than the sun for the first time. So we not only see black holes, but we can see also stars now. And of course, this type of star is easier to resolve because after the end of hydrogen burning, the envelope expands up to several astronomical units. And the most striking feature when you look at these two pictures is that these cool evolved stars have a photosphere which looks much more granular than the sun's photosphere. But like many stars, these two ones turn out to be in binary system. So this evolutionary track in black that you see in the Hertzsprung diagram, in the Hertzsprung-Russell diagram in the back, is valid for isolated stars. But how does binary evolution affects this evolution? Through mass transfer or mass loss. So mass loss, for instance, is what's responsible for the enrichment of the interstellar medium in dust and in complex molecules. And this evolution and like the mass loss aspect is also important from the point of view of the star, because for massive stars, you want to know whether they lose enough mass or not to form a compact object through core collapse supernova after a while. And concerning the really big picture, it has an impact further downstream on the merger rates you compute for the coalescence of double compact object mergers, because some of this binary where you have a massive cool evolved stars are believed to be potential progenitors for this double compact object merger that we detect now through gravitational wave interferometry. And so now let's zoom out from this photosphere and look at what's going on at a much broader scale. So thanks to ALMA exquisite spatial and spectral resolution, we could look at this cool evolved stars with the ALMA Atomium program led by Len Dessine in KU11. So through spectral imaging, we obtained this multi-channel molecular line emission maps that you can see here with red and blue indicating blue shifted and red shifted components. So they are at a much broader scale as the previous one, but you recognize Pi1 GRU, which was also one of the two pictures I showed you on the previous one. So as you can see, non-spherical morphology are very common, and it's more and more often ascribed to the presence of an underlying companion too dim to be directly detected. So the whole question I'm going to try to address in this talk is, can we set constraints on the properties of the companion and on its orbits based purely on the morpho-kinematics of the circumbinary envelope that we can obtain with ALMA. So the main physical difficulty is in this system is that the physical the launching mechanism of this dusty wind is still largely unconstrained. It's probably due to a combination of stellar pulsation in the innermost regions and of radiative pressure on dust grains farther downstream in the wind. So numerical simulations like this one by Ben Freitag shown that the granulosity I told you about is due to convective cells in the deepest layer. Then pulsations are going to lift the material up to distances where the temperature is low enough that molecules and then dust grains can form. So growth of dust grain depend not only on the thermodynamical conditions set by the stellar wind radiative field, but also on the chemical contents of the gas. Indeed, oxygen-rich AGB stars are going to form oxygen-rich dust grains, which have a much lower opacity than carbon-rich dust grains. So you have oxygen-rich AGB star, carbon-rich AGB stars, and you expect a different properties for the wind around this object, because the way they couple to the radiative field is going to be different. So once you form this dust grain, you can couple to the continuum radiative field from the star, and the dust grains are going to be accelerated through radiative pressure and distribute their momentum through in the ambient gas that they drag along. So here and we expect like different things for carbon and oxygen rich stars. So that's also what we want to investigate here. Are we going to have different morphology when we have a companion, depending on the chemical composition of the outflow? So the model we designed was like a simplified model of the wind launching mechanism in this configuration. So I'm going to show you numerical simulations where I solve the hydrodynamics equations in this configuration, where you have a donor star, so either an AGB or red supergiant or red giants, and here a companion, which can be a stellar companion or a substellar companion, so potentially a massive planet. Then the forces applied in the simulations are going to be the one associated to the Roche potential. We have the co-rotating frame, so you're going to have non-inertial forces, and the wind acceleration. So the wind launching is ensured by this continuum opacity. So we can discuss later on, if you want, like the detail of this launching mechanism, but it's based on combinations of different opacities at different dust condensation temperatures. Then for the thermodynamics, the cooling of the gas itself, I assume that I'm working with a polytropic thermodynamical evolution and a polytropic index, such as we match the observations in terms of temperature profile. And here in this model, you can show that the key parameters which are going to define the shape of the solution, so the morphology of the envelope, are typically the chemical composition of the wind, which is going to play a role in the wind acceleration. And in the case of an oxygen-rich AGB star, you're going to have an acceleration which is more progressive, because the dust grains have more troubles to couple to the stellar radiative field. And then a key quantity is going to be the wind speed. So this V infinity, which is the terminal wind speed, compared to the orbital speed, which is going to be the orbital separation times the orbital angular speed. The mass ratio between the first body, the primary body, so the cool evolved star, the donor star, and the orbiting secondary, and the filling factor. So how big is this donor star compared to its Roche lobe? So the Roche lobe being defined as the sphere of gravitational influence of each body. We run 70 different simulations, so 3D simulations. I spare you the details on the numerical setup, but we can discuss this later. We have a grid now of simulations for different parameters, and they give different morphology. And the idea was to compare then this morphology to observation to constrain the parameters of the secondary. So when we look at the very innermost region of numerical simulations, here I take a fiducial numerical simulation where we see on the left the donor star, the cool evolved donor star. On the right, at the center right here, you have the secondary, so either like a main sequence star, a white dwarf, an exoplanet. And in yellow, you see in semi-transparent and in opaque yellow, two different isodensity surfaces. So the classic morphology that we have at this scale, which is typically the orbital scale, is a wind which is compressed toward the secondary, with this pinching right here near the innermost, the inner Lagrangian point. You have a disk which can form on the secondary, and that I'm going to detail a bit more in a minute. And you have this spiral arm, you have this accretion wake actually, which is going to seed at a much broader scale the spiral arm. So this scale is typically of the order of a few AU, sometimes a few 10 AU, but a scale which is too small to be directly imaged. I remember the pictures I showed in the introduction, we were more dealing with hundreds of astronomical units. So we have to look at what's going on at a much broader scale. And the interest of this numerical setup is that there is a very huge dynamics between, we can really go from this orbital scale up to much larger distance. So first, let's look at what's going on around the secondary. So this wind capture disk that I mentioned. So the secondary is going to accrete a fraction of the dust-driven wind from the donor star, and provided the wind speed is of the order or smaller than the orbital speed, then you can have enough angular momentum in the accreted flow to form a centrifugally maintained structure around the secondary. So this kind of disk around the secondary might actually be then the launching test bed, the launching background for an outflow, so typically through magnetocentrifugal effects. And that might be what we observed in this system in L2 where Pierre Cavella and collaborators identified a few years ago a plume coming from a position which was not the position of the red giant. And later on, they identified with ALMA planet candidates, which was at the location of the plume. So this plume might be something which is a collimated outflow coming from this disk surrounding the planet candidate. So now let's zoom out and look at what happens at a scale where we can actually see what's going on with ALMA, like spectral imaging. So here you remember this nice postcard. Now this nice postcard is the very innermost region of this simulation space. And here I have another isodensity contour with the orbital angular momentum along this axis. And you see that at large scale, you get this flattening of the wind in the equatorial plane. So that's simply due to the fact that the secondary is massive enough to produce a wobbling motion of the primary, of the cool evolved star, around the barycenter, around the center of mass. And this wobbling motion is going to imprint to the dust-driven wind at a much larger scale, this flattening of the structure. And the main consequence of this is that if you overlook this flattening, if you assume that the distribution is isotropic around the star, the mass loss rates you're going to derive are systematically overestimated. And in this paper, we evaluated by which factor and showed that the superwind phase is probably an artifact of this flattening, this equatorial density enhancement of the wind, which has been overlooked. Now about the different features in terms of morphology that you can identify in these systems. Well, here, if I'm plotting like the density map face on, so we are looking at here in the plane, you have the orbital plane, and you see the two bodies in the very innermost region. You see this spiral forming from the accretion wake of the secondary. So that's what I told you initially. This this accretion wake is going to form a self-similar spiral at a much broader scale, up to several 10 orbital separations. You also see here a main difference between the carbon-rich and the oxygen-rich environments. In oxygen-rich environment, this more progressive acceleration tends to blur the pattern, so you get something which is less sharp and more difficult to identify. And you can check, because there are 3D simulations, the influence of the line of sight by looking at this configuration from another point of view. So now we no longer look at this spiral, so same simulation as this one, but we no longer look at the spiral face on, but now we are edge on. So you can see here the mesh of the simulation space, the grid we use. And you can see still this, this density distribution where you get these arcs, these successive arcs around the main system. So depending on the line of sight, spirals and the spiral shock can manifest as arcs.
2 minutes.
2 minutes? Fine. So last comment about the binary envelope morphology. I told you that the whole interest of this procedure was now to set constraint on the underlying companion. And here we are typically in this situation with CW LEO, a system where 2 different teams had very different orbital separation for the secondary that we don't see in this system. And by comparing this to this grid of simulation, we could deduce that this orbital separation was much too low and could not reproduce the observation. So why this one was actually reproducing something pretty similar, which is given right here. So this petal-like pattern around the system, which is just due to this accretion wake being disrupted because the wind speed is a bit lower compared to the orbital speed is a bit higher. So this ratio is a bit lower overall, and then the wind has more troubles to escape the system. And you retrieve this kind of petal-like pattern in other systems. So here I've told you about density maps, but that's not what we are looking at, right? We are looking at synthetic molecular line emission maps. So to produce synthetic observables from the simulations, we followed this procedure. We use the 3D hydro distribution. We use the chemistry profile for the fractional abundance of CO, for instance, obtained by Marie van de Sand at K11. Then it gives you in each point of your simulation space the mass abundance of each species, and you get the kinetic information in terms of speed. So you can use a radiative transfer code like the code Magritte developed by Frédéric de Coster to produce a synthetic multi-channel molecular line emission maps here for a CO rotation level. And so you can look for the different Doppler shift at what your simulation look like. So here that's the proof of principle of the procedure you can follow to extract from this simulation synthetic observables. And I'm going to conclude with this animation, which is just an animated version of the picture I showed you. So we can reproduce the different features that we observe in these systems, provided we really sample like the parameter space I showed you with this velocity of the wind compared to the orbital speed, which is really one of the key. You have systematic difference between carbon-rich and oxygen-rich environments. You have the possibility in some cases to form a disk around the secondary, which might lead to a structure like the plumes, and which could be also a way to indirectly detect the presence of a companion. And from the simulations, you can extract synthetic images by combining this to chemical networks. So now the perspectives are to include the dust in the simulations, to have like a realistic representation of the dust, to work on eccentric orbits, so like alternative orbits, to look at the impact of lower mass objects, so ready to see whether you could still get a significant change in the morphology with an exoplanet, and to look at the influence of triple systems, so like a third companion in a hierarchical configuration. And I'm going to thank you for your attention and take questions and comments.
Thank you very much. That was very interesting and such beautiful simulations. Nice to see that they agree also so nicely with the observations.
Thanks.
Are there any questions yet in the chat?
Not yet, but I have some questions.
Okay, go ahead.
Yeah, but if the chair has questions, can go ahead before me. But
no, go ahead.
So I wanted to ask, so just very basic question, but just to fully understand. So this spiral streamer or spiral arm that it's creating, or this is just because the secondary is moving within the wind of the main star, and then it's getting mass from the gas, the material that it's in the wind, right?
Good question. That's the point I tried to make on this slide. You have two effects. You have on one side the direct gravitational influence of the secondary, which is going to deflect the flow toward it and produce this accretion wave that you can see right here. Okay, and you have the indirect effects of the secondary, which is that because of the presence of the secondary, the primary is going to move around is going to wobble around the center of mass. So even if you had like an isolated star, which would, for a magic reason, wobble around virtual and artificial center of mass, you would still reproduce these kinds of things, right? So the spiral pattern itself is something which is related to the wake right here, so directly to the influence of the secondary, but the flattening itself is due to the wobbling motion of the primary, which is also induced, of course, by the secondary.
Okay, thanks. So there is one question in the chat. It's thanks for the impressive results. I wonder in general how the separation between the two objects would affect your results, as I imagine the angular momentum introduced would be different.
Yeah, so that's really like this key parameter right here. You can rewrite it like this V infinity over A omega. You can see it also as the quantity of kinetic energy per unit mass, which is deposited in the wind by the launching mechanism, whatever the launching mechanism, okay? compared to the amplitude of the Roche potential. So how deep is the gravitational potential from which you try to extract yourself. And provided, so this quantity is higher than the orbital speed, then you can really get out. So if you have like an orbital separation which gets smaller and smaller for comparable masses and configuration, you're gonna get an orbital speed which gets higher. And then because like the wind speed is always between 15 and 30 kilometers per second for this type of dust-driven winds, depending on the orbital separation, you might get like different morphologies. And the morphologies which are the most disturbed, like the petal-like patterns, are typically the ones for low ratio. So for low ratio, so configurations where your orbital separation is low, because then you want like you want a high orbital speed.
Okay, thanks. There is time for wait. We can pause them on Slack, I guess.
Yeah, I think we should put the other questions on Slack, and I think we need to move on to the last speaker of this session.